Hello, this video covers section 12.5, and in this section we're going to be looking at some of the different applications of both exponential and logarithmic functions. I think it's one of the more interesting sections because many of the contexts that we are going to be looking at are things that we have experienced in the real world or have heard about. So the very first one is the idea of interest. You know, when we invest money, it earns interest, it earns money on the principal or the amount that we've deposited. And so this first formula takes a look at what we call compound interest. All right, so the compound interest formula. It says if P dollars are deposited in an account that pays annual interest rate R that is compounded n times per year, then the amount A in the account after T years is given by the formula that we see right here. It says the amount P is referred to as the principal. You may have heard that term before. P is the initial investment, the principal. The annual interest rate is often reported as a percent. Okay, so it must be converted to a decimal number for this formula. For example, if it gave us that R was equal to 5%, we would need to write that as 0.05, write it as a decimal. And the other kind of important thing that may or may not be familiar in here is the idea of compounded n times per year. There's some different terminology that goes with that we want to mention at this point. Different values. Sometimes it might say compounded annually. If it says compounded annually, then n is equal to 1 because it only compounds once per year. If it says semi-annually, then that's twice per year, so n equals 2. If it says quarterly, how many quarters in a year? Should be 4, so that means n is equal to 4. We could say compounded monthly, which there's how many months in a year? There's 12, so n would be 12. We could say weekly, which there are 52 weeks in a year, so n would be 52. And the last one I'm going to write here is we could say interest is compounded daily, which would mean n is 365, not accounting for leap year. So you're going to want to become familiar with those words. Any of those words could be used in a problem, and I think you probably pretty much already know what those words mean, but if not, there they are for your notes. So we have an example here. It says Yukari invested $8,000 in a savings account that pays 3% annual interest compounded quarterly. If she does not withdraw any money from this account, how much will be in the account after 5 years? So if we write down, first of all, what we know, or what we're given in the problem, we're given quite a few things. It says that he invested $8,000. Well, that's the principal, that's the initial investment. So we know that P is equal to 8,000. And it says it pays 3% annual interest. That means R is 3%, but we want to write that as a decimal, so 0.03. It also says compounded quarterly, and we saw above that when it's compounded quarterly, that means n equals 4, because it compounds 4 times per year. And it says if she does not withdraw any money from the account, how much money will be in the account in 5 years? So we just saw the time. The time is 5 years, and we're trying to find the future amount. Remember from our formula up here, the future amount is A. That's the amount after T years. So the part we're trying to find is A. And so if we plug everything into the formula here, we get that A is equal to our initial investment P, which is 8,000 times 1 plus R, which is 0.03 divided by N, which is 4, raised to the N times T, so 4 times 5. Hopefully that makes sense. So we could clean this thing up a little bit maybe, simplifying what's in the parentheses first. 1 plus 0.03 divided by 4 is about 1, or is exactly 1.0075. We might want to rewrite this power. Instead of 4 times 5, change that to a 20. And now it's going to be really easy to calculate this with our calculator. We can put it all in at once, or we can do it in multiple steps. If you have a graphing calculator, it's really easy to put it all in at once. We just take the 8,000 parentheses 1.0075 raised to the 20th power. And since we're talking about money here, we probably want to round to 2 decimal places so we can take care of pennies. So it would be $9,289.47. $9,289.47. This is dollars. Let's put the appropriate symbol on there. Now, let me show you some other ways we could have calculated this. You actually, in the graphing calculator, you can put all this in at once. I could say 8,000 parentheses, I could say 1 plus 0.03 divided by 4, and I could raise that to the 20th. Or even in parentheses, I could put 4 times 5. Make sure I get all that in there. I get the same answer. Some of you may elect to do this in steps. So like I could go 1 plus 0.03 divided by 4 to get that inside, and then I could raise that to the 20th, and then I could multiply that by 8,000. That may be a little easier to do it this way for those of you that don't have graphing calculators, to do it in steps. So do basically the inside part of the parentheses first, then raise that answer to the 20th power, and then multiply that by 8,000. Notice all 3 ways I just showed you came up with the same answer. This section is going to be extremely important that you know how to work calculators to do calculations. Alright, so here we have another example of working with compounding interest, just like the last example, although we'll see here in a little bit that the problem is a bit different. And look, we're going to start out by doing like we did in the last problem. We're going to write down what we're given. And that's always good to go through that problem solving process. And so if we write down what's given, we should probably first read the problem. It says Steve deposited $10,000 in an account that pays 6% annual interest compounded quarterly. How long will it take until there's $25,000 in the account? So as we go through this, the first thing we see here is this 10,000. What does that represent? Well, if you look back up at your formula at the top of the page, we have A is the future amount, we have P is the initial deposit or the principal, we have an interest rate of R, we have a number of times the interest compounds, which is N, and we have a time or number of years that the interest is being or that the money is being invested, and that would be our T. Well, when I see that 10,000, it says that's what he deposited. So of course that's our P. Our principal is $10,000. When we move on to the next given item, it gives us this 6% here, which we know that of course to be the rate or the R. Remember to write it as a decimal. Things won't work out if we don't move that decimal place over twice. The next thing it says is compounded quarterly. Well, we know that to be the N. What value of N is it? if interest compounds quarterly, well, there's 4 quarters in a year, so that would be that n was equal to 4. Is there any other given information? Well, you should see that in the last sentence it asks how long will it take until there's 25,000 in the account. Well, that 25,000, that's some future amount, so that's the A that is given. So in this problem is definitely different than the last one, because the last one we were trying to find the A. This one we're given the A. What is it that we're trying to find? What about this problem tells us what it is that we're looking for? Because that's our next thing to write down. And hopefully you say T, because this little phrase right here, when you see how long, that's saying what is T equal to. Other phrases that say how long are things like when, or you might even include the word after how many years. So just keep that in mind as you're moving forward. So the thing that we're trying to find is that fifth variable we don't know what T is equal to. So let's go ahead and put all our given information into the compounding interest formula. We know that A is 25,000 in this problem, is equal to P, which is 10,000. And then we take times 1 plus R, which is 0.06, divided by N, which is 4, raised to the N times T. Remember, N is 4, so this is 4T. Okay, so notice there's only one unknown variable. It's this T right over here. That's what we're going to have to find. And we've only done this a few times, solved equations like this in previous sections, but we have to be able to solve now an equation where the unknown variable, in this case T, is up in the exponent. And the process we go through with that is to remember that first we need to isolate the exponent. We need to isolate the exponent. And of course how we do that is, in this case, we're going to divide by 10,000 on both sides. Because if we divide by 10,000, then those go away on the right hand side, and 25,000 divided by 10,000 is 2.5. And then I suppose we could simplify over here if we wanted to, this inside part that's left over. The base of the exponent is basically this 1 plus 0.06 divided by 4. If you do that calculation off to the side, 1 plus 0.06 divided by 4. 0.06 divided by 4 is 0.015. If we add that to 1, we get 1.015. So this equation is going to look like 1.015 raised to the 4t. Now, if you remember back to the previous section, section 12.4, we had a step that we wanted to do here that helped us get this 4t out of the power. You remember what it was? We wanted to apply the natural log, or it could be any old log. I generally choose the natural log. We want to apply that to both sides. So if we do that, this is going to look like the natural log of the right side equals the natural log of the left side. This is the natural log of 2.5 divided by the natural log of 1.015 raised to the 4t. Remember, the advantage of this is that we can use the power rule and bring that 4t to the front, which is a big advantage. We're going to now apply the power rule, because that helps us get the 4t out of the power. And so that gives us now the natural log of 2.5 equals 4t, now it's on the front, times, I put a little dot there. We don't have to put it there, but just to help us remember that this is times 1.015. And then now we're actually really close to being able to solve this problem. Remember, we're trying to get t by itself, and we have t here times 4, and then t times this natural log. Well, anytime we want to undo multiplication, we just divide. So since it's multiplied by 4, how about we divide by 4? And since it's also multiplied by this natural log, let's divide by natural log of 1.015. Of course, we know with equations, if we do it on one side, we also have to do it on the other side. That's not a big deal to remember. And then over here, 4's divide out, the natural logs divide out, and voila, we have t by itself. And the other side, we can just do in our calculator. So if we pull up our calculator, we can take the natural log of 2.5, and you have to be careful here. We can't just say divided by 4 times the natural log of 1.015, because the calculator knows order of operations, and what it's going to do is divide by 4 first, and then take that whole answer and multiply it by the natural log of 1.015, which we don't want. We want to divide the whole thing by 4 and by the natural log. So I think the easiest way to get around this is just to go back here and say, put another divide sign there. That tells us to multiply or to divide ln 2.5 by 4 and by the other natural log. So if I do that, I get this answer, about 15.386. Another way you could calculate this, though, is you could say natural log of 2.5, and then you can say I want to divide by the denominator, but I know the denominator has more than one operation, so we can put the denominator in parentheses. I can take 4 times the natural log of 1.015 and then close up that set of parentheses, and you'll see we get the same answer. So we get the answer is about, I should say approximately, 15.4. So our answer is 15.4 years is about how long it takes for the money to grow to 25,000. Okay. We can take a look at another formula here. Another interest formula we sometimes see is what's called the compounding, but it's continuous compounding interest. And it says if P dollars are deposited in an account that pays an annual interest rate R that is compounded, notice it says here, continuously. We haven't seen that word continuously before. Then the amount A after T years is given by this formula. Okay, so if we see, anytime we see the words compounded continuously, we want to use this formula. And the words, all the letters still really represent the same stuff. P is still the principal, just like the last two problems. A is the future amount, R is some rate, and T is some time. Let's see how this works. See in the next example that if $10,000 is invested in an account that pays 7% annual interest, compounded, there's the key word there, compounded what? Continuously. That means we need to use this formula. It says how long will it take for the investment to double? So let's write down what it is that we're given. developing good problem-solving habits here. So if we say given, again, $10,000 invested. $10,000 is the principal, the initial investment. It says invest in an account that pays 7% annual interest, so R is 0.07. Compounding continuously. How long will it take for the investment to double? So here, it's a little bit different in the wording from the last problem. It does use that word how long again, so we know that what we're trying to find is T. We don't know T. But it says the investment will double. Remember last time we started with 10,000, just like this one, but we grew to 25,000. If it doubles, what's that future amount A? It's not 25 this time. It's twice 10,000, which is, of course, 20,000. So we can go ahead and write this information in this formula, and we see that 20,000 A would be equal to P, which is 10,000, times E to the R, which is 0.07 times T. And again, notice that there's this unknown variable up in the exponent. But we now know how to solve this. Remember, our first step is to isolate, so we can divide both sides by 10,000, which gives us a nice round number of 2 on the left-hand side, equals 0.07 T. And again, just like in the last problem, we can take the natural log of both sides. But because this uses an exponent with base e, something very nice happens on the right-hand side. You remember how this works from the last section? So we have ln 2, but on the other side, remember that the ln of e to the x is just what? It's just x. Because natural log and e to the x, they're inverse operations, they're inverse functions, they wipe each other out or they undo each other. And so in this one, all that's left is the exponent, the 0.07 t, which is very, very nice because how much work is left? Almost none, really. All we have to do here is divide by 0.07 and we're done. It's very nice. So if we go ahead and calculate this, natural log of 2 divided by 0.07 is 9.9. So t is about 9.9 years. In fact, we really just learned a new formula that we could use here in the future for continuous compounding interest. The time to double is given by the formula t equals the natural log of 2 divided by, what was it divided by? ln of 2 divided by 0.07, which was the rate, so r. And likewise, we could talk about the time to triple, which, what would be different in that case? In this case, the money started at 10,000 and grew to 20,000, but if it tripled, then it would grow to 30,000. So we'd have 10,000 equals 30,000, and then after our initial step of dividing both sides by 10,000, we'd have 30,000 divided by 10,000, which wouldn't be 2, it would be 3, of course. So the only thing different would be here that we have the natural log of not 2, but the natural log of 3 divided by r. Nice little formulas. Now you don't have to remember those, but it's a nice little shortcut. One thing I do want you to remember is that this only works in the case that we have continuous compounding interest. You can't use these formulas for regular compounding interest. Okay, so now we get into some more interesting problems. There's many places in the real world where we can talk about exponential growth. And the formula you're going to see is very familiar because it looks a lot like the one we just looked at for continuous compounding interest. The only thing is that it uses some slightly different variables. So it says if a quantity increases at an exponential rate, its size p at time t is given by the formula p equals p0 times e to the k times t, where p0, that's been p in our last problem. P0 is the initial size of the quantity. That could be the initial population, the initial amount of some substance, could be anything. And k represents the exponential growth rate. We'll notice where k is. K is like the r in the last problem. There's the r. K is a lot like that. So let's see how this might work for a problem. Example below says in 2000 the population of a town was 72,000. By 2010 the population had grown to 150,000. If the population continues to grow exponentially, what will the population be in 2018? Alright, so again, if we write down what's given, it says in 2000 the population of the town was 72,000. Well, what is that? That's the initial population. That's the P0, 72,000. It says by 2010 the population had grown to 150,000. That's some future population, which in this case is not A. It's not a future amount A like in the compound interest problems. It's this letter P. So the future population is 150,000. And what else is given? It's not obvious maybe right off the bat, but we should be able to see here though the time, because in 2000 was when it was 72,000. In 2010 it grew to 150. So how many years was that? Well, I think it's pretty obvious to see that it's 10 years, but we could write it down. The time here is the difference between 2010 and 2000, which is of course 10 years. And if we look up at our formula, we know P, we know P0, we know T. What we don't know is K. And what is the question asking us? It says if the population continues to grow exponentially, what will the population be in 2018? So eventually what we're trying to find is the population in 2018. But we can't do that yet. In fact, all these population growth problems require 2 steps. The thing we don't know is how fast this population is growing at. So we can't figure out what it's going to be in 2018 if we don't know the rate at which it's growing. So the 2-step process is that first we got to find out what k is equal to. And this is going to look a lot like the last problem. If we go to set up the equation using this formula based on what we know that 150,000, some future population, is equal to the initial population of 72,000 times e to the k, which we don't know, times t, which is 10. So look at this. It takes 10 years for 72,000 to grow to 150,000. And we've solved this now quite a few times. We're going to isolate the exponent first. We're going to divide by 72,000 on both sides. Okay, and when we do this, this leaves us e to the 10k. And 150,000 divided by 72,000 is about 2.083, and the 3 repeats. And then we know that the next step is to we got to get access to this 10k, which is in the power, and so we take the ln of both sides. So we have the ln of 2.083 equals, and we know when we ln this side, the e cancels with the ln, and we just get 10k. And then, of course, we can divide by 10 to get k by itself. And this will give us what k is equal to. Now, it's very important that you watch and pay attention here to what we're going to do on the calculator, because it's the last calculation we did to get the 2.083. This is not an exact number like 1.5. This is 2.08, and then the 3 continues to repeat. So every time you round, this is important to know, every time you round, you lose accuracy. And so we don't really want to round to the very end. I don't really want to write this as 2.083 because the answer is not 2.083. It's 2.0833333 and so on. So what we want to do is use the calculator's memory tool. We want to use the fact that the calculator stores this value, the whole value. And the way we do that is we say natural log, and then we don't just want to type in 2.083. We don't want to do that. Instead, what we want to do is we want to get the previous answer. And the way you do that is you first hit the second button, the yellow button, and then right here where the negative button is, there's 3 little letters above it, A and S, which stands for previous answer. And so if you hit that button, you get A and S in there. And I want to take the natural log of my previous answer, that 2.083, and I want to divide it by 10. And that gives me my growth rate. My growth rate k is about 0.073. Again though, notice that it's not exactly 0.073 because the decimal place continues to go on. So I'm going to have to use that value, the stored value, the A and S. I'm going to have to use that in my future calculation. But we definitely finished the first step of this problem. We found out the growth rate. We found out what k was equal to. K is about 7.3%. Now we can go ahead and answer the question, what's the population in 2018? And so, of course, that is telling us something about t. How many years does it take to get to 2018? Well, that's 2018 minus 2000, which is, of course, how many years? It's 18 years. And so if we go back to this formula one more time, what we see is we don't know p. P is now what we're trying to find. We want to know the population in 2018. We do know that it's initially, though, it's 72,000. We do know that the growth rate is 0.073, and we know that it takes 18 years. Or we want to find out what it will be in 18 years. So really now we can just go ahead and plug this into the calculator. There's nothing to isolate because p is already by itself. That's what we're trying to find, some future population. And so we just go back to our calculator and we take 72,000 times e, to the 0.073. But do we want to use 0.073? Remember, that's not accurate. That's a rounded value. Instead, we want to use this whole answer. How do we get that? We hit second answer, and it puts in that whole value times 18, close parentheses. We want to have the answer times 18, or that 0.073 times 18 in parentheses, because that whole calculation there is in the power. It's e to that whole power. And so, what's that future population? It's 269,000, basically 835. 269,835 people in 2018. Or about 270,000 people. But this is how we tackle population growth or any sort of growth. It also turns out that we kind of do the same thing when we have decay problems. So that's the next example, solving exponential decay problems. And notice the formula is exactly the same. We still have an initial amount, we have some future amount p, we still have some rate, except the k in this case is going to be some negative k because we're decreasing or we're decaying the amount of substance or that we have, and then t is still the time. So if we look at the example here, it says that strontium-89 has a half-life of 50.6 days. And it says how long will it take for 20 grams of strontium-89 to decay to 8 grams. And we have some new terminology in this problem. We've never before talked about what half-life means. So let's go ahead and define that. Half-life is defined as the time it takes, I would add this to your notes, the time it takes for a substance to decay to half of its original amount. It's how long it takes for whatever it was, however much there was initially, to become half of what it initially was. So if we start out by writing down what's given, remember this is always a good idea. It says it has a half-life of 50.6 days, so that's time. Time is 50.6. And remember, it's 50.6 days is the amount of time it takes for the initial amount to become half of that. What's the initial amount? What's the P0? Well, it says 20 grams, right? That's the initial amount. And if it decays to half of that, that means the future amount P is going to be half of 20, which is, of course, 10. And then what we want to find is the time t, because it says again how long here, time it takes to decay to 8 grams. And again, kind of like the last problem, this is a two-step problem. We got to first find out what k is. We don't know our decay rate. So if we write down what's given, we know that in the future, because we're decaying, 20 grams will decay to 10 grams, and it takes 50.6 days at some growth rate k to do that. So we go through the same process. You're probably getting tired of seeing this by now, but you should be getting really good at doing it. 10 divided by 20 is of course 1/2, or we can write it down as 0.5 equals e to the 50.6k. Of course, we take the natural log of both sides, so we have the natural log of 0.5 equals, and remember what happens on this side, natural log of e, those cancel, and we just get 50.6k, nice and easy. And we divide by 50.6. And when we do that, we get what k is equal to. Natural log of 0.5 divided by 50.6 is about negative 1.3%. I'm going to write negative 0.013. Let's write 7. Okay, so we do see it's decaying. Again, that growth rate is negative. That shows that we're decaying and not growing. So now we move to the second step. We actually solve the problem. How much time t does it take to decay to 8 grams? So instead of the future amount being 10, so we're not talking about half-life anymore, we're talking about decaying to 8 from 20. Initial 20, future 8 equals e times the k, negative 0.0137 time. We don't know time. So this is going to require us to go through that same problem we just went through before one more time. Divide by 20. Divide by 20. We could get a decimal for this, but I'm going to just go ahead and leave it as 8 over 20. Well, we could reduce it since 4 goes into 8 twice and 4 goes into 25 times. We could rewrite it as 2/5 equals e to the negative 0.0137t. And of course we take the natural log, so the natural log of 2/5, natural log cancels the e here, equals negative 0.0137t, and we divide to get t by itself, negative 0.0137, both sides. Now, when you do that, okay, we have natural log of 2 divided by 5, and then we want to divide by that negative 0.01. Oh, be careful. We don't want to use this value because that's a rounded value. What do we want to use? We want to use our previous answer. So we don't lose accuracy in our answer. We don't want rounding error. So if we do that, we get about 66.9 days, which I think sounds like a pretty reasonable answer. Okay, so our next example here talks about tuition, which should be of interest to you since you're a college student. It says in the United States, the average tuition and fees charged by a 4-year public college can be described by the function, and it gives us that f of x is equal to 2,398 times 1.05 to the x power. So we're not having to write down or come up with our own formula. We're given a formula. It says x represents the number of years after 1992, and it says use this function to predict when the average tuition and fees will reach 10,000. Okay, so use this function to predict when. There's that word when. What does that mean we're trying to find? We're given something, and we're trying to find something. Word when is one of those keywords. It means we're trying to find time. when tuition and fees will reach 10,000. And remember that this function describes the tuition and fees, so it's telling us that the y value, or the f of x, is equal to 10,000. It's kind of like some future value. In fact, we can compare this to the formulas we've been looking at. It basically looks like 2398, that's the initial tuition and fees in 1992, and then f of x, that's like our future p. So when we go to write in our formula here, we're going to have the future amount, that's what we're growing to, is equal to 2398 times 1.05 to the x power. Now what do we do after this? How do we solve something like this? Is it really any different than the last examples we've been looking at? Well, hopefully you say the answer is no. It's not any different, because what do? We need to isolate the exponent. We need to divide both sides by the 2398 to get that exponent by itself. Now the right hand side is just 1.05 raised to the x power. We're going to get something ugly on the other side. 10,000 divided by 2398 is going to be some kind of ugly decimal. Let's just write 4.17. And then how do we get at this x? What's our tool? Take the ln of both sides. We have the ln of the left side and the ln of the right side. ln of 4.17 equals the ln of 1.05 to the x. And now this doesn't have base e, so the ln doesn't cancel over here, but we can remember use what rule? We can use the power rule. Don't forget about that. I know all these things keep on happening over and over again. You got to remember these few important tricks. So when we do that, we get the ln of 4.17 equals x times the ln of 1.05. Now we're really close, because we can just go ahead and divide both sides by the ln of 1.05. Because that'll get x by itself. So, okay, remember to use, we don't just want to use 4.17, we want to use this whole thing. So we want to take the natural log of second answer, and we want to divide that by natural log of 1.05. And we get about 29.3. Now, I guess if we go back here, this shouldn't have been t, this should have been what x is equal to, because x is the number of years. And when it says when, we haven't really solved the problem yet, because this is 29.3 years. That's 29.3 years after when? After 1992. So I want to take 1992 and I want to add to it 29.3, which puts us in the year what? Well, one of the things we want to do here is we probably want to think of this, since it's more than 29 years, it's going to be into the next year, so we could think of this more as like 30 years. And if we add 30 to 1992, this puts us in the year 2022. You could say 2021, but let's go ahead and say 2022 is what year it'll take for tuition to reach $10,000. Our last couple of log applications here. One thing you may have heard of is pH, pH tells us whether a liquid is acidic or basic or neutral. It says determine the pH of a solution whose concentration of hydrogen atoms is 3.98 times 10 to the negative 7 moles per liter. And we have some formula here for calculating pH. It says the pH of a liquid is calculated by the formula pH of negative log of this H+, where H+ is the concentration of hydrogen ions in moles per liter. So this is very simply just calculated. We're given what H+ is. We're given that H+, that's the hydrogen ion concentration. We're given this problem that it's 3.98 times 10 to the negative 7. And so to calculate the pH, we're just going to take negative log, this is log base 10, of 3.98 times 10 to the negative 7. Not too bad. Easy calculation. We pull up our calculator. So we go negative log, and we do need to put scientific notation, so let me show you how to do this. We're going to say 3.98, and then scientific notation, the easiest way to do it is that EE button right here, right by the comma. It's 2 capital E's, so if we go second EE, and then we write a negative 7, close the parentheses, it tells us our pH is about 6.4. Now the other way we could have calculated those, we could have also said negative log 3.98, and we could just specifically write it out, times 10 raised to the negative 7, and that'll give us the same answer. I think there's a little bit more to type in that way, but you can also do it that way. This is a pH of 6.4. So we just found that the pH is 6.4. Let's go ahead and think about what that means. I found a pH scale here on the internet, just doing a Google search, and what we see here is that pure water, that's when pH is 7, that's neutral. Anything above 7, 8, 9, 10, all this stuff in this range is considered basic. And then stuff below 7 is considered acidic, battery acid being the most acidic. And so we had a 6.4. We are basically in between, not quite neutral, a little bit more acidic than urine, and a little bit less acidic than milk. Milk 6.6. And so if you want to just add that to your notes, 7, if pH is equal to 7, that's neutral. If pH is greater than 7, that's basic. And if pH is less than 7, that's acidic. So in this case, this is less than 7, so this is slightly acidic. Okay, and then the last one is sound. One of the ways we measure sound is in decibels. And so the volume L of the sound in decibels is given by the formula L equals 10 times the log of I over 10 to the negative 12. It's this formula here, where I is the intensity of the sound in watts per square meter, and the constant 10 to the negative 12 is the intensity of the softest sound that humans can hear. And so it says the volume of a machine is 90 decibels. Find the intensity of a sound with this volume. So we are basically given what L is. We're given the volume. We're given that L is 90 decibels and we want to find the intensity. We want to find what I is equal to. So this is really just an application of what we've been doing. We know we have that formula up there, so L is 90 equals 10 times the log of I divided by 10 to the negative 12. And I want to solve for I. Well, we need to get the log by itself. How do we get the log by itself? Well, we need to isolate the log by dividing by 10. So we can divide both sides by 10, which gives us 9 equals the log I divided by 10 to the negative 12. Now that we have the log isolated, we put it back to exponential form. The base here is 10, so it's the base raised to the power of 9 is equal to our argument, I over 10 to the negative 12. So how do I get I by itself? I need to multiply both sides by 10 to the negative 12. Because that'll cause these powers to cancel. So I get I is equal to 10 to the negative 12 times 10 to the 9. We can add the powers there. We get 10 to the negative 3. Which is about 0.001 watts per square meter. And that does it for this problem and this section. Thanks a lot. We'll see you in class.